So at the very start of this course, we discovered that the mechanics of particles was often best expressed using a Lagrangian and a principle of least action. And indeed, we discussed how you could generate the Lagrangian for single particles, built out of the kinetic energy minus the potential energy. Now we've been dealing with things more than just single particles. We've been dealing with fields. Now a field is a lot like a lot of little particles. If I imagine a field diagrammatically as here's a sort of field in two dimensions, x and y, and so my z direction is my phi of x and y, then I can imagine my field being defined by the values on a grid. So the fact that I know how to generalize this principle up to lots of particles, you think I might be able to describe fields. So I have all my values on grid points, and I can construct my action as before, except now I have my Lagrangian as a function of lots and lots of different parameters. Instead of a single Euler-Lagrange equation, I end up with a full set of Lagrange equations to describe each one describing all my free parameters. So indeed I might have, even in the grid case, I might have a countably infinite number of them. And in the continuous case, of course, I'll have an uncountably infinite number of variables and equations. One of the problems with doing this, of course, is that I no longer have an immediate instinct on how to generate my Lagrangian, because my Lagrangian is no longer for a single particle, so I can't just say it's the kinetic energy minus the potential energy. And there's another far deeper problem with this kind of formulation of Lagrangians for a field. Suppose I was talking about an electromagnetic field. And indeed, the most compact form we can get that, we know, is a 4-vector field. So for each point in space-time, I need 4 variables. Well, I could put that on a grid and I could write it like this, but there's a kind of an obvious problem with that. You might even be able to think of more than one. Have a go before we go on.